Okay, so welcome to today's lesson. This is Tutor Poul from IQ Academy. Okay, and I would like to congratulate you guys for making it to semester 2 of your pre-med journey. Okay, I urge you to continue working hard because semester 1 it was challenging, yes. Okay, but I can assure you that semester 2 comes with its own weight as well. Okay, so even semester 2 is going to be very, very, very challenging. So it requires that you put in your extra effort from the start. Not by yourself, Kamanji last core exam, you start pushing, no. So you're supposed to put in seriousness right from the start. Okay, so as you begin your semester, as you begin your studies for semester 2, make sure that from the word go, you try by all means to understand the concept, you try by all means to study. Okay, so once again, congratulations for making it to semester 2. And this is our first ever class for semester 2. So as always, I will urge you to be interactive, to be free. If I explain anything that you do not understand, please, please, please just unmute your mic and ask me. Okay, I'll be very happy to help. Okay, so we are doing this topic called atomic structure, which is the first topic in semester 2. Okay, so this is the topic that we are doing. Okay, so we're not slide. Okay. Okay, let's start moving. Okay, so we are looking at atomic structure, and in these lessons, I've outlined the objectives that we have to do by the end of this lesson. Okay, so the first one is we have to define what atomic structure is. Okay, we know it, and then we look at the revolution of this atomic structure. Okay, because different scientists had their say about this atomic structure. And then we look at the electromagnetic radiation, which involves the electromagnetic spectrum. We look at a wave and its characteristics. Okay, some say a wave and its properties, which are just wavelength, we have frequency, we have amplitude, we have wave speed. Those are the things that we are going to look at. And then we'll also look at the speed of light and its applications. And then finally, we look at the exam sample questions. Okay, yeah. So atomic structure, you can see it on your screen. So the first thing is, what is atomic structure? Okay, so atomic structure is just simply a structure of an atom. Okay, the atom as we know it. Okay, so we know that the atom or the atoms are composed of mainly 2 regions. Okay, and what are those regions? We know that the prominent one is the one in the middle, which is just the what? The nucleus. Okay, so in red there, you can see I labeled the nucleus. And then the outside there where we have electrons, we'll just call it as the electron cloud. Okay, later on when you talk about the evolution, you get to understand better what this electron cloud is. Okay, so electron cloud is simply a region that surrounds the nucleus, okay, where you are likely to find your electrons. Okay, so that's the electron cloud. So if I use the knowledge for semester 1, we say that around this nucleus, we have those energy levels, right? So I can have an energy level like that. Then I have another one like that, just like that, right? We know this atomic structure from even biology, okay? So this is what atomic structure is. It's just the study of the composition of an atom, which consists of the nucleus and the electron cloud. The electron cloud, we are just saying it's a region where you are likely to find your electrons. Okay, so this is just me illustrating more. We know that when I draw an atom like that, okay, in the nucleus there, you'll find two subatomic particles, right? Which are the neutron and the proton. And then around this nucleus, we'll find electrons that are evolving. Okay, so that's the structure of the atom. And then this is the same illustration I'm showing here. Very good illustration. Okay, it's the same thing here. And then I also want us to revise a bit. So the atom has a certain representation. Okay, so I have X there, which will represent the symbol of that atom or that element, right? So I have a big X here that represents the chemical symbol. And then on top of this symbol, we have what we call as the mass number, right? And the mass number, we know that it's just the addition of the neutrons to the what? To the protons. Okay, so the proton number is represented by the letter Z, and then the neutron number by the letter N, and then the mass number is represented by the letter A. So I'm sure you remember this from the isotopes. Yeah. And then the Z, which is down here, which is the subscript, okay, represents the number of what? Protons, okay. And we know that in a neutral atom or in a neutral element, the number of protons, they should always be equal to the number of what? Electrons. This we know, right? No wonder the electrons have a property that they can be neutral because you have equal charges of the positive charges, the equal charges of the negative, right? Okay, so that's just a summary. And then this is the exact thing I was explaining. Okay, and then here I have the nucleus and the structure of the atom, where we have the relative charges and the relative mass. So we know that the electron there, it has a relative charge of -1, and then the proton is a +1, while a neutron has a relative charge of 0. Okay, and then the relative mass, those are the relative masses there that you have for these subatomic particles. Okay, and then now we go to the evolution, meaning the history, how these different scientists, what say did they have on this atom? Okay, so it began in a very long time ago with a scientist that we call as Democritus. Okay, so Democritus had his own view, and then from his view, Dalton developed the view. Then came Thomas. You can see from Democritus, we come to Dalton there, and then we had Thomas. We have Rutherford, and then we have Bohr. Okay, so the model for the Bohr is the very common one. Okay, everyone should know the Bohr's model. Okay, and then after the Bohr's model, now we have the modern one. Now that we have the present model of the atom. Okay, so the modern quantum cloud model that was discovered post 1930. Okay, so it's very important, I repeat, it's very important to know the contributions of each and one of these scientists, okay? Because you have questions, they will just ask you like, what was the contribution of Dalton to the atomic structure, okay? So you have to know what is the constitution of Bohr to the atomic structure, you have to know. Okay, so let's go through their contributions, which are just these ones here on your screen, okay? So the first one, the first scientist there, he had a belief of atomism, okay? So atomism simply means that this Democritus guy, or this Democritus scientist in the 5th century BC, okay? He believed that all matter is composed of small particles that we know as atoms, okay? So he believed that the smallest thing you can ever find on Earth was the atom, Okay, so he believed that all the matter, meaning everything that we use, the shoes, the clothes, the wall, everything was composed of small particles that were called what? Atoms. That was the view for this Democritus guy. Okay, and then from this guy, the development continues. We had another guy called John Dalton, okay, by the year of 1803. Okay, so him now, he expanded what Democritus had already said, okay? So Democritus said the atoms are the smallest particles, and then this John Dalton guy, he came and he added on, he said these atoms, of course, they are small, okay? And apart from being the composition of all the matter, they are also the composition of the compounds, okay? So if, for example, in sand, you'll find certain types of atoms. In metals, you find certain types of atoms. So if you get those two things that are different, you combine them. It means the atoms from those two different things will combine to form the new thing, right? Okay, so that's what he said. So that was the contribution of John Dalton there. Okay, he said the atoms are indivisible, and the compounds and the compounds are the combinations of different types of atoms, right? So if, for example, let me give an example of water. Okay, so water is just a combination of oxygen and hydrogen. So to get water, you need to combine the atoms of the oxygen and the atoms of the hydrogen, right? So that was the contribution of this John guy. And then development continued to J.J. Thomson, okay? So Thomson now, he came with his own view that we call as the plum pudding model here on top. The plum pudding model, where he said that the atom, okay? He said that the atom is just a sphere, okay? And those positives and the negative charges are just embedded on that sphere. So you know a sphere, right? Like something that looks like an egg, okay? So he said the atom was something that looks like an egg, which is a sphere. And then on that sphere, we have positive charges and negative charges. That's what this Thomson guy said the atom was. So that was his contribution. So you should be able to differentiate the contribution that each and every one of these made, right? Okay, and then from there, we continued to develop, okay, until we reached on this scientist who is known as Ernest Rutherford, okay? So Ernest Rutherford, what was his contribution? Okay, so his contribution is termed as the nuclear model on top here, okay? So what does that state? Okay, so it states that the electrons that are around the nucleus of an atom, okay, they move or they orbit in fixed paths, okay? They move or they orbit in fixed paths. You can see an illustration on this diagram, right? So if I have a nucleus in the middle there, which has positive charges, and then you can see that the electrons are moving around this nucleus in fixed paths like that. You have another electron moving like that, another one moving like that. You have another one which is moving like that in that direction, and another one that's moving like that. Okay, so electrons orbit in a set predictable paths around fixed positively nucleus. So this was the contribution of Rutherford. And then now we go to the common person, who is Niels Bohr. Okay, the Bohr's model. Everyone should know this because from grade 12, we use this Bohr's model, right? Okay, so Bohr's model simply states that we have electrons revolving around in concentric circles or in energy levels. You can even see here. So you have positive charges, and then electrons are moving in energy levels like that. So that's the Bohr's model. That's his contribution. And then from there now we moved on to the quantum model. where we are saying that the location, okay, of these electrons that are moving around this nucleus is not specific, okay? It's not specific, like it just moves in this energy cell like that, no. So this quantum model says no to that. And it was headed by a scientist called as Ewin Kondinga, okay? So that was his name, okay? And that year was 1926, okay? So if I can read here, they're saying the locations of the electrons could only be described as part of the cloud around the nucleus, but you can't know the specific location where the electrons are, okay? You can only know that those electrons, they are in this region, but you can't predict exactly where in this region the electron is. So that's what the quantum is, right? Okay, so this is the evolution. So you have to take time to just know the contribution of this, because you might not know what questions may come. Okay, and then here I was putting the notes now on each one individual scientist. You can take a look at them or upload the notes on Drive. Okay, so this is Democritus, his contribution. We have John Dalton, Thomson. If you want to see them, I even included their pictures there. Okay, and then Ernest Rutherford, you have James Chadwick. Okay, so James Chadwick, he was a student for Ernest Rutherford. So he was working together with this guy. So if they ask you the contribution of this guy known as James Chadwick, okay, it's the same contribution as Ernest Rutherford because they are working together. Okay, and then we have Niels Bohr, who is this guy here, if you ever wanted to see Mr. Bohr. Okay, and this is his contribution. I've explained what it means, and then this is Ewin Kondinga with his contribution as well. I was further explaining here. Okay. All right, and then here I also put a summary, just like in the first place. So you can take a look at this, and then you just memorize them, right? You memorize like this one did this, that one that did that, just like that. Okay, so very simple to follow. And then we move on from the evolution, we go now to electromagnetic radiation. Okay, so I don't know if there are any questions. If there are any questions, just unmute yourself and you're free to ask. Okay, so we now talk about electromagnetic radiation. Okay, so what is electromagnetic radiation? So here I've put a picture that describes what electromagnetic radiation is. Okay, so on this picture, you can see that I have an electric field, and then I have a magnetic field there. Okay, so a magnetic field will be moving in that direction along this axis that we can see. And then as it moves, it will be moving together with the electric field. Okay, so the electric field is in red, and then the magnetic field is. So as they are moving, okay, it means that they are transferring energy from this point here to wherever they are going here. Okay, so electromagnetic radiation is just simply a means, okay, of transferring energy from one place to the other. Okay, I think I put the definition here. So here they are saying energy that travels through space in form of waves is called electromagnetic radiation. Okay, so I can have energy here, and this energy wants to move from this place all the way up to there. Okay, so if it's moving in space, it means that it will travel through what we know as electromagnetic radiation. Okay, so electro means there's a presence of the electric field there. Then the magnetic means that you have the magnetic field there, and then they're traveling in a certain direction. Okay, so I hope you get. So electromagnetic radiation is just what? The energy that travels through space in form of waves. Okay, with its combined form of electromagnetic field and magnetic field. Okay, and then here I was trying to elaborate more, I put another definition. I'm saying an electromagnetic, and then here I'm specifying as a wave is just the fundamental concepts, mostly in physics, but even in chemistry we can use it, representing the propagation, okay, the propagation of electric and magnetic fields through space. So propagation simply means the movement or the transportation of this electromagnetic and of this electric, I mean, and the magnetic fields through space. So as those fields are traveling, they carry with them energy. So energy is being transported from one place, let's say this place, to the other place like that, okay? So that's what we call an electromagnetic radiation or an electromagnetic wave, okay? So we have a lot of them, the electromagnetic waves, okay? I was giving examples here. So I was saying they include radio waves. We can see microwaves, okay? Not a microwave that is in your house, no. A microwave now, that is electromagnetic radiation. So we also have infrared, we have visible light, we have ultraviolet, we have X-rays, and we have gamma rays. Okay, so of all these 7 electromagnetic waves, the one that is not harmful to the not let me say not harmful, but the one that is most useful, okay, is this visible light, okay? Because without visible light, then all of us on earth will be blind because we couldn't see. In short, it will be dark anywhere. So when God said, "Let there be light," okay, he meant this electromagnetic wave that we are calling as visible light, so that we can see. So it's very important for you to see the screen there where you are. It's because of this visible light, okay? So you can see that our life is just based on chemistry, right? Or physics. Okay, so this visible light is very important. And when we talk about the electromagnetic spectrum, you see that visible light has a separate spectrum on its own. Why? Because it's very, very important for us to see colors. This is purple, this is blue. It's because of this visible light there. Okay, so these are examples of the electromagnetic waves, and they play a crucial role, okay, in our daily lives. So for visible light, everything that we do for light to be there, okay, it's visible light. And then for the radio waves, for you to see, not to see, but to hear what I'm saying here, okay, for you to hear what I'm saying here, is because of these radio waves. They are transferring my voice, okay? So my voice is being converted into an electric energy, okay? And then it passes through these radio waves, I mean, and then it comes to you and it's converted back to sound energy so that you can get me, right? Okay, so they are used in communication. When you call someone, those are radio waves. When you listen to the radio, when you watch TV, okay? And then I can also give an example of X-rays, okay? X-rays, you are all familiar. When you go to the hospital, maybe they want to see your lungs or your internal organs, okay? They will do that scan, they call the X-ray, all right? Okay, so it's very useful in the medical field, okay? You can also see here in optics, even when you want to see like those who have challenges with their eyes, yeah, something like that, okay? So there's an aspect of the electromagnetic waves for it. Applied in those spectacles. Yeah, okay, so those are some of the uses. Here I was defining the same thing that I was explaining, okay? And then now, those examples of the waves form what we call as the electromagnetic spectrum, okay? They form what we call as the electromagnetic spectrum. So this electromagnetic spectrum, it's arranged in an orderly way, okay? Later on, you'll see that it's arranged according to the increasing frequency or the decreasing wavelength, okay? So when I explain those concepts, you will see them, okay? So when you combine all those electromagnetic waves and you put them together, you form what we call as the electromagnetic spectrum. Okay, so the electromagnetic spectrum has gamma rays, X-rays, ultraviolet, infrared, microwave, and radio. So there are 7. Okay, and then this visible light here, I said it's very special, right? Because you can see that it's part of the electromagnetic spectrum, okay? But on its own, again, it forms a spectrum of colors. This one here, those colors you see on the rainbow, okay? I don't know if you know this mnemonic, okay? We say Roig beam, okay? So these are the colors on the rainbow or on the electromagnetic spectrum. So we start with red, orange, yellow, green, blue, indigo, which is very close to purple. And then we say violet at the end. So you can see the colors, the order I've written, they are going like this, right? You have red at the far end there, and then you have violet at the far end there. Okay, so it's very important to know about the visible light spectrum. So I think I put it on the separate here. Yeah, so I'm saying when you combine those electric waves, you form this electromagnetic spectrum, where the only difference is the type of radiation in their wavelengths. Okay, so I was saying they are arranged in such a way that starting from the radio waves all the way up to the gamma rays. Okay, so these gamma rays here are starting from radio waves to the gamma rays. Okay, you are going in an increasing frequency. So the frequency increases of these waves here. And then from the gamma rays to the wavelength, not to the wavelength, I mean to the radio waves, you see that the wavelength decreases. Okay, but I know maybe it might be confusing to me because I haven't yet talked about the frequency and the wavelength. So I'll talk about it again. Okay, so these are the types of the electromagnetic radiation and their uses here. I also put their uses here so you can read on your own. You can see X-rays, what I was explaining here, right? Okay, and then the visible light, this is the light spectrum where you have colors, the Roig beam. You have red, orange, that's the light spectrum, okay? I was putting it very clearly here, you can see it, right? Okay. Okay, so this is the same thing. It's just the visible light spectrum that I was showing you. I was trying to demonstrate. So each, an important thing to note is that each of these colors, okay, it has a certain value for the wavelength or a certain range of the wavelength. So some question they will ask you, such light was passing through what, find the wavelength, and then tell us the cloud of that light, okay? So you have to know these ranges here that you can see here. You have to know that from 625 to 590, that color should be orange, okay? Or from 625 to 740, that color should be red, okay? So they will ask you to find the wavelength. Then after you find the wavelength, they will tell you what color is that, okay, based on the wavelength. So the visible light spectrum is very important. So you have to know these ranges for the colors. You have to know, okay? So the smallest one there will give you violet, okay? And then 500 to somewhere 435 there, it will be, this is indigo, right? So it will be indigo. Then 520 to 500 blue, okay? So when I was in first year, the only one that I mastered was this. I just knew it's between 520 and 500, it's color blue, okay? So you can find different ways of mastering it, okay? And then now we can talk about what waves are, because we said all those are waves, right? Yes, they are waves, but what are they? What is a wave? Okay, so a wave is just a disturbance that carries energy through matter and space. Okay, so the electromagnetic waves, they only travel in space. And then The waves, okay, the waves, they can travel in space and through matter. So when you hit, maybe you hit a drum, those drums that they play. So when you hit it, for it to sound, okay, it's because of the waves, the disturbance that you've caused by doing on the drum. So is that it? Yeah, because it's because of those waves that are carrying energy or that are causing a disturbance. Okay, so a wave, it's just a disturbance that carries energy through matter, space. Okay, so these waves, they transfer energy without altering the matter. So this is a very important point because it can come in, it can come as a question. So waves transfer energy without altering the matter. Okay, so what does that? I mean, not altering, without transferring the matter. What does that mean? Okay, so if I say I have a metal here like that. Okay, if I have a metal here and I put a candle here with a lighting there on top, it's burning like that. Okay, so this heat that this metal will start receiving here will start slowly by slowly to be going like that until it reaches there. Okay, so when you just put the candle here and you touch this side here, it will be cold, like you won't be burnt. But after some time, if you come and touch here, you find that it's very hot. So how has that happened? It has happened through a wave. So a wave of heat has been moving through this matter like that. But the matter itself is not moving. It's just seated like this. It's static, right? Yeah. So that's a very important property of a wave. It can transfer energy without transferring the matter. Okay. So after some time you touch here, you burn yourself. Yeah. Okay, I think that is a good example. Okay, so waves are produced by something that vibrates. Okay, you can also take note of that. And then I was trying again to define what a wave here, which is just a disturbance that transmits energy through matter or space. Okay, and then we can talk about the parts of the wave. So this is a representation of the wave. This is how it looks like. You can draw an axis there, and then you draw a wave that goes like that. Okay, so this wave has parts, very important parts that you have to take note of to enjoy your atomic structure, the topic as in general. Okay, so this is just an introduction. Okay, so the bottom part there, or the lowest part of this wave is what we call as a trough. Okay, so I was labeling it there as a trough. And then the highest part there is what we call as a crest. Okay, so this is a crest. Even that one there is a crest. Even that one here is a crest. But the lowest part is what we call as a trough. Even this one, we call it as a trough. Okay, so I was defining here. So crest, top of the wave, trough, bottom of the wave. And then we have what we call as amplitude. Okay, so if you did trigonometry, we know what amplitude is, right? It's just the height, okay? From the point of rest to the highest point from the point of rest to the lowest point. Okay, so meaning if this is my point of rest to the highest point like that. Okay, so this distance here from this point of rest, okay, to there is what we call as the amplitude, or some people, you can define it as the height of the wave from the center line, which is the resting point, right? Okay, so that's what the amplitude is. And then now we have the wavelength. Okay, so what is the wavelength? So the wavelength is simply the distance between two troughs or the distance between two crests. Okay, and it's denoted by this symbol, okay, which we call as lambda. Okay, lambda. Okay, so wavelength is denoted by lambda, and it's just the distance between two troughs like that. Or, these are crests, two crests or two troughs like that. Okay, so from the highest point of this wave to the highest point of the cave, of the wave, I mean, that is what we call as the wavelength. From the lowest point of this wave to the lowest point of the wave again is what we call as the wavelength. Okay. Okay, and this is the same thing here. I was just trying to illustrate more. Okay. And then now we talk about the characteristics, okay, of which wavelength is one of them. So characteristics of waves. So we have one, the wavelength, okay, and we know the wavelength is just the distance between two troughs or two crests, right? Okay, so it is represented by lambda and it is measured in meters. A very important piece of information to know. Okay, so this wavelength is measured in meters. This is the standard unit, okay, meters, except for the wavelength, okay, except for the wavelength of the light spectrum. So the light spectrum, that spectrum that had orange, those colors, right? Its wavelength should always be in nanometers, okay? So whenever you calculate the equation, you find your wavelength in meters, change it to nanometers because you are talking about the light spectrum, right? Those colors, the red, the blues, yeah. And then we have another characteristics, which we call as frequency, okay? So the frequency is just the number of waves, okay, that passes a given point per second, okay? So if I have, let's say this is my point here, okay? So the frequency is how many waves are going to pass through this point per second. That's the frequency, okay? So if I have waves that are coming like that, passing through this point, how many of these waves are going to pass this given point per second? Okay, that number of waves that passes through that point per second is what we call as the frequency. Okay, so the frequency is measured in units which we call as hertz. Okay, they are represented by Hz or s to the power minus 1. So s to the power minus 1 is also written as the s, like that. Okay, the s or s to the power minus 1 or hertz. So you can choose any of those three to represent the units of your frequency. Okay. Sometimes the questions will require you to change them into kilohertz. Okay, but since we did the metric system in semester 1, we know how to convert to the kilo, right? Yeah, so we just divide by 1,000, then we would have converted to the kilo. Okay, and then the amplitude, simply the height of the wave, the wave, okay? And then these two properties here, the frequency and the wavelength, okay? They are directly, oh, no, they are inversely proportional, okay? Meaning if you have a very big wavelength, you're going to have a very small frequency, okay? And if you have a very small wavelength, it means you are going to have a very big frequency. So they are inversely proportional, okay? And when you multiply them, you will get what we call the wave speed. So for you to calculate the speed of the wave, you just calculate your value. You just multiply the value of your wavelength with the value of the frequency. Okay, I think I have an illustration here. So these are the characteristics. What is the wavelength? I was showing it here on its own, but I've explained what is a frequency and its SI units. Okay, and then this is what I was explaining. I was saying wavelength, which is represented by this lambda symbol, okay, and the frequency, which is represented by F or, okay, V. So the frequency is represented by F or V. Take note, right? So in physics, when you say V, then you would mean velocity, right? Yeah. But in chemistry, and especially this topic, atomic structure, the V represents the frequency. Okay, so take note. V represents the frequency, or you can put the F there. And then the speed of the wave of the wave is represented by C. Okay, so take note of the differences, right? The speed is represented by C, the frequency by V or F, And then the wavelength is represented by lambda. Okay, so this is what I was explaining. I was saying this wavelength here and the frequency, they are inversely proportional. So you can see that the one that I have down here, it has a longer wavelength like that. Okay, so if it has a longer wavelength, it means the frequency will decrease. Because if I have a point here, okay, because these wavelengths are so big, it means for this curve to come here and pass, it will be taking a lot of time, right? So leading to less waves that will be passing through this given point in 1 second. So it means the frequency will reduce. But if I have a short wavelength like here, it means these waves will be passing tap on this point, right? Capita wave, capita, it will be passing just like that, right? Okay, so meaning you have a higher frequency, but the wavelength will be shorter. So they are oppositely, they are inversely proportional, I mean. Okay, then this is the same illustration that I was saying here. Long wavelength, it means you have low frequency. Then high frequency, it means you have short wavelength there. Okay. Okay, so we continue. Okay, so this is me trying to show the inverse proportion of the frequency. So if I can bring back the electromagnetic spectrum, you can see that from the radio waves here to the gamma rays, the frequency will be increasing. Okay, the frequency will be increasing. So if the frequency is increasing, it means the wavelength is what? Is decreasing. Okay, so the wavelength here is short. No wonder the frequency is no wonder the frequency is increasing. Okay, you can even check the values here. So you have 3 multiplied by 10 to the power 9, 3 multiplied by 10 to the power 12, 3 multiplied by 10 to the power 16. So you can see the frequency is increasing, but the value of the wavelength, which are these values down here, you can see they are decreasing because this is 10 to the power 0, which is just 1. And then I have 10 to the power minus 2, which will just be 0 point something something. And then I have 10 to the power minus 4, which will just be 0 point something something. So you can see that as the wavelength decreases, okay, the frequency increases. So they are inversely proportional, right? And then the opposite happens. If I start from here, I'm going this side, it means I'm increasing my wavelength. Okay, I'm increasing my wavelength. Then it will mean that the frequency will start decreasing like that, right? Okay, so take note of that. And then this is just this the same spectrum, but here I want to emphasize energy. Okay, very soon we'll be talking about the Planck's constant and the like. Okay, so you have to know that energy. Okay, so the value of the energy follows the frequency. Okay, so if frequency is increasing, it means energy is increasing. But remember, the wavelength is what? Decreasing, right? Okay, so frequency goes with the energy. If the energy is a lot, it means the frequency will be a lot. So imagine you are, what can I say? Imagine you are writing, right? If you increase the energy of your writing, you'll be writing very fast, right? You'll be writing very fast, such that in a second you would have written a lot of words, right? Because what the energy has increased. Okay. Yeah. Okay. And then now we talk about the wave velocity. Okay, or the velocity of waves. So I said that if you multiply the value of the frequency to the value of the wavelength, then you will get your wave speed. Okay. Okay. So wave speed, I said it is represented by C under this topic. Okay, it's just equals to what? Just equals to frequency, which can be represented by F or V multiplied by the lambda, which is the wavelength. Okay, very important equation to know. Okay, so master this equation and how to get the subjects. Okay, you can be given the speed, the wavelength, and then you find the frequency. So you can be given the frequency, the wavelength, you find the speed. That's it. Okay, so it's important to note that the speed is measured in meters per second, the frequency in hertz, and then the wavelength in meters. Okay. Okay, so this is the same thing that I was doing, and then we can talk about the speed of light. Okay, so speed of light, which is represented by c, which is just the speed of the wave, is equals to the frequency multiplied by the wavelength. Okay, so we know that the speed of light has a constant value, which is just what 3.0 multiplied by 10 to the power 8 meters per second in a vacuum. Some they write it as 2.99. Okay, 2.997 multiplied by 10 to the power 8 meters per second. Okay, so it would depend with what your lecturer will want you to use. Okay, so if you want the 2.99, make sure you use the 2.99, right? If you want the 3.0, make sure you use the 3.0. Okay, because if you use this in a question and then you use this in a question, the answers will just be slightly different. Okay, so make sure you use the one that he recommends. Okay, so that's the value there. And then now we can look at example questions actually of using this formula given different things. Okay, so I have an example here. Okay, so example, they're saying, what is the frequency of yellow light? Okay, given that the wavelength is given as 556 nanometers. Okay, so the secret is always to convert these units, the nanometers, you convert them back to what? To meters. And we know that 1 nanometer is equals to what? Okay, 1 nanometer is equals to 10 to the power minus 9 meters, right? Okay, so metric system, semester 1. Okay, conversion factors, you have to know. So nano means 9. Okay, so if I have 1 nanometer, it will just be 10 to the power minus 9 meters. Okay, so make sure you convert your wavelength to meters. Okay, and then here they are asking what is the frequency. So you notice that in the question they will not mention anything about the value of the speed, because they know that the value of the speed is always constant if it's the speed of light. Okay, so here they're even saying yellow light. So by the fact of them saying yellow light, it means that this is light, and the speed of light is just 3.00 times 10 to the power 8 meters per second. Okay, so it means we are going to use this as our speed, and then this wavelength that they have given us from nanometers, make sure you convert it to meters. Okay, so just divide by 10 to the power 9 nanometers, or you can multiply by 10 to the power minus 9 nanometers. It will just be the same. So the value of the wavelength now in meters is this. Okay, and then now you can get that formula. We saw that the speed of light will just equals to what? The frequency, which is f or v multiplied by the lambda. So here we're given the lambda and the speed of light. We want to find the frequency. So it means the frequency will just be equals to what? The speed of light over the wavelength. So this is exactly what I was showing here. So you can see that I put the speed of light on top, and then I'm dividing with the wavelength. Okay, so after I divide that, I get this as my final answer: 5.4 times 10 to the power 14 hertz. Okay, so if you want here, you can put s to the power minus 1, or you can just put the second. These are also the units for frequency. Okay, but the recommended one, just put hertz there. Okay, so another example using this same formula here on your screen would be this one here. They're saying speed of light calculations. They're saying if I have a wavelength, okay, of 685 nanometers, okay, what will be my frequency, which is the V there, okay? So this is the speed of light. So we know definitely that the value of the speed will just be what? 2.00 times 10 to the power 8, right? So we're just dividing the speed with the frequency. So make sure you change from nanometers, we're changing to what? Meters. So meaning we are multiplying this number by 10 to the power minus 9, conversion factor, right? Okay, so when I divide these two numbers on my calculator, I'm getting this as my answer. Okay, then this is another calculation. You still use the same formula. I've put a lot of calculations here just for your practice. Okay, so I was also putting the answers there. Okay, this is another question. So you can go through this. You can go through this. Okay, so I want us now to solve just one sample question, then we can go it a day, right? Go it a day. Just wanted to introduce the topic. So exam sample questions, okay? So I was getting these questions from the tutorial sheets. Okay, so we have the first question there from tutorial sheet 1. They are saying the brilliant red colors seen in fireworks, okay, are due to the emission of light with wavelengths around 650 nanometers. When strontium salts, such as this salt here and that salt, are heated, this can be easily demonstrated in the lab by dissolving one of these salts in methanol that contains a little water and igniting the mixture in an evaporating dish. Okay. And now they're saying calculate the frequency of red light of wavelength 6.50 times 10 to the power 2 nanometers. Okay, so we know how to do this. We know how to do it. So we just have to apply this formula. C is equals to the frequency multiplied by lambda. Okay, so here I think calculate the frequency. Here I'm calculating it. So V will just be equals to what? The speed of light over the lambda there. Okay, but we have to make sure that this lambda is in what? Meters, because here it has been given in nanometers. So we have been given 6.50 times 10 to the power 2 nanometers, or we can just use this value here, 650 nanometers. So 650 nanometers, we have to convert it to meters. So how do you convert this? We'll just say the same number multiplied by 10 to the power minus 9. So multiplied by 10 to the power minus 9, this will now become meters, okay? So here where there's nano here, that's where we have put 10 to the power minus 9. Then the M will flip here, okay? So that will be our frequency, I mean our wavelength, okay? And then we can now combine it with the light to find the value of the frequency. So frequency will just be equals to what? Just be equals to 3.00 multiplied by 10 to the power 8, which is the speed of light, divided by the 650 multiplied by 10 to the power minus 9. Okay, so what do you get there? Let me see. Okay, where is it? Okay, so I have 3.00 times 10 to the power 8. And then we are saying that number we're dividing with what? Okay. Calculator is not working. 3.00 times 10 to the power 8. Okay. Okay, and then we're dividing by 650 multiplied by 10 to the power minus 9. Okay, so according to my calculator, I'm getting this value. I'm getting 4.6. If I round it off, it would be 4.62 multiplied by 10. Okay, to the power, how many decimal places? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so I'm moving 14 places. So this will be 14 hairs. Okay, so that is our frequency there using our formula. So you can be given any of the two to find the other one. Or in short, you can be given one because we know that the speed of light is a constant value. So you can only be given either the frequency to find the wavelength or the wavelength to find the frequency. Okay, so do I have any question?
I have a question.
Yes, you're free to ask.
So, how do you know which one to use? Because we were given the first wavelength for around 650. Then we also have a wavelength down there, 6.50.
Okay, so those two wavelengths are actually the same. So this one here is the same as this one. This one down here has just been put in scientific notation, if you have noticed. They have just moved the point from, this is 650, so they have moved the point 1, 2. So it has become 6.5. And then they have put times 10 to the power 2, which is the same as 650, right?
Yes.
Yes, so it is the same value. So in converting, you can use any of them. It will still give you the same answer.
All right, thank you.
All right. Okay, so I've put other questions here, which we'll discuss as the semester goes on. But as a glimpse of what you are expected to know, you can always pass through. So you can see here we have been given the wavelength, we are calculating the frequency again, and then there are some definitions here. Name the 3 primary characteristics of waves, okay? So we said frequency, wavelength, and then the speed, right? Okay, so these are the 3 characteristics. And then in the next lesson, we are going to learn what this is, explain the dual nature of light. That says that light can exist as a particle and it can also exist as a wave. Okay, so we explain this. But for the sake of practice, you can actually solve some of these questions. Like here, they have given us the frequency here, you can see, and then they're asking us to calculate the wavelength. Okay, so we know that the speed is constant, it's just 3.10. So we can apply that formula. I've put a lot of questions here. Some of these are based on those scientists I was explaining here, you can see. They're saying, what are the contributions of these guys? John Dalton, I talked about him, Thomas, Rutherford, Niels Bohr. Okay, so you can go through the question. Okay, start practicing now, and then I have this question here that they're saying, give 3 examples of electromagnetic radiations. Okay, what we did, we had radio waves, gamma rays, X-rays, visible light, infrared, ultraviolet. Okay, so you can give any of those 3. And then the others here, they are for calculations. Like this one, you have been given the wavelength, you're calculating the frequency. Even here, I'm sure you're calculating the frequency. Okay, so that's that for today. We can go through this when I upload on time. Okay, do I have any other question? Before I close the class. Okay, no question. All right, so we'll continue our classes. tomorrow I think we have, I don't know. I think it's biology. I don't know. Yeah, I'll check the timetable. So thank you so much and have a blessed night.
Same.